a new series called Study With Me, where we are going to give our best and try to have revision for specific chapters. We know that your science exam is coming up, and for that purpose we will be revising chapter 11, which is electricity, and chapter 12 a little bit with magnetic effects of current. So let's start going. So this is for grade 10 CBSE board, and let's start with chapter 11, electricity. Electricity is nothing but flow of electrons. Whenever we have imbalance of electrons, so for example, if one side has excess electrons and other side has lack of electrons, then we have this electricity going. Electricity can be broadly divided into static electricity, where we actually, for example, in winter when you touch the doorknob, you feel a static current. This is electrons accumulating on doorknob. But what we are studying in this chapter is current electricity, where the electrons are actually flowing from negative terminal to positive terminal. But the sign conventionally accepted thing is we say that the current flows from positive to negative terminal, but in reality electrons are flowing from negative terminal to positive terminal. We will start with the discussion of some key parameters which are required in this chapter. The first one is charge, which is denoted by letter Q. The unit is coulomb, which is most of the units in this chapter are in recognition or in honor of scientist names. So these names which are seeing for units, they are actually names of the scientists who have significant contribution in this field. Charge is denoted by Q. Its unit is coulomb. The fundamental unit of charge is the charge of electron. Remember, electron is always negatively charged, so it's minus, and it's 1.6 into 10 to the power negative 19 coulomb, which is a very tiny charge. Do not forget this negative 19 as a power. If you write that as a positive 19, that's completely wrong. It's a negative 1.6 into 10 to the power minus 19 coulomb. Second quantity which we are encountering in this chapter is voltage. Voltage is denoted by V, and its unit is volt, again name of a scientist. The third one is current, which is denoted by either lowercase I or uppercase I, it doesn't matter. The unit is ampere. And the last one, slightly rare, is work, which is defined, which is used in the definition of voltage. So work done, that is also used in heat release in the heating effect of electric current, and its unit is joule. Now let's see the first formula. Current is nothing but flow of electron in unit time, so it will be Q, which is charge, divided by time. So the first formula is ampere, which is current. Current is equal to charge divided by time. Now the same formula can be expressed as in slightly different format. You can say Q is equal to I times T, which is cross multiplication. That is perfectly alright. The second formula is used in the definition of voltage. A volt is defined as work done when you move a unit charge from infinity to that particular point, and for that purpose it is work divided by charge. So voltage is work divided by charge. So V is equal to W divided by Q, or again you can cross multiply and you can write as W as V times Q, which is also perfectly alright. Now next we are going to see Ohm's law. Ohm's law says that voltage and current are directly proportional to each other. Now let me remind you that Ohm's law is not universal. It is mostly applicable for metallic conductors. There are certain conductors which do not obey Ohm's law. That's electronics, which when we will see diodes, mostly semiconductor diodes, transistors, thyristors, they do not obey, they do not follow Ohm's law, but that's like electronics engineering. If you study electrical engineering, mostly you deal with like metallic conductors which follow Ohm's law. It says that voltage is directly proportional to current, and When two things are directly proportional to each other, that means their ratio is constant. So we can say that voltage divided by current is that ratio is constant, and that is the resistance of that conductor. So V divided by I is R. Now there is another subtopic which is like factors on which the resistance of the conductor depends. Resistance of a conductor depends upon the length of the conductor. Obviously, if you take longer length of a conductor, then the electrons will encounter more resistance because of the longer length. So resistance is directly proportional to the length of the conductor. More the length, more is the resistance. And then the second factor which is going to depend upon is resistance is inversely proportional to area of cross section. So when two things are inversely proportional, you write them with the same proportionality symbol, but we write them in one numerator and one denominator. So now resistance is 1 over area. Now if you double the area, then it will be easier for electrons, because now they have think about like more area of cross section. Now they will have less resistance because it will be easier for them to flow. If the area of the cross section increases, the resistance decreases. You can combine these two things and you can write them in one single format. This is resistance is directly proportional to length but inversely proportional to the area of cross section of that conductor. If you want to eliminate that proportionality symbol, you can take equal to, but now we have to introduce something called rho. It's a Greek symbol. Rho is nothing but specific resistance of that material. In your textbook, they have given you the standard value of specific resistance is material property. Conductors will have specific resistance very low, insulators will have very high. Some specific values are given in the table. Please take a look at them. With this one, now we are going to go to electrical symbols. Electrical symbols, the first one is battery. We have to purposely show the one line. Now the longer line is representing positive terminal, the shorter line is representing negative terminal. Please do not connect the horizontal lines. There must be a gap to indicate the separation of the two terminals. Also, if you show these two vertical lines with exact same length, then again that's wrong, because that represents capacitor, which is totally different element. In battery, you have to have two dissimilar lines, one slightly longer representing positive terminal, another slightly shorter representing negative terminal, and there should be some gap in between them. If you have a series of batteries, then multiple batteries, then you can show them like this one. Make sure that all longer lines should be connected, indicating towards left direction, or they all must be towards left or all must be towards right. You cannot mix them. Here, if the longer line is towards left, here also the longer line should be towards left. Otherwise, the batteries are contradicting with each other, and that's kind of wrong. So the next thing which we are going to see is key, which is used to connect or disconnect the circuit. The key will have two positions. The close position will be like this one, that will allow the electrons to flow through the circuit, and open key kind of represents a disconnected circuit, so that will be shown without the dot. There are two instruments which are particularly mentioned in this chapter. One is voltmeter, which is used to measure the voltage across the two terminals of a particular resistor or any 2 points. Voltmeter is connected parallel to the element across which we are connecting, measuring the voltage. So voltmeter is connected in parallel. The second instrument is ammeter, which is used to measure the ampere, which is nothing but current, and that has to be connected in series or in line. Resistors are shown by a zigzag line, and you can have a single resistance or you can have multiple resistances connected in series. If they are connected end to end, then that will be series resistances. In that case, the equivalent resistance or the total resistance of the series combination will be simply addition of the individual values. There is one more way to connect the series the resistors, then that will be in parallel, and in that case they will be connected. All the one ends will be connected to the on the similar terminal, and all the second ends will be connected to another terminal. And in that case, this will be referred as parallel combination. In parallel combination, the effective resistance of the parallel combination is given by 1 upon R is equal to 1 upon R1, 1 upon R2, 1 upon R3 added together. Remember, R1, R2, R3 are the individual value of the resistance, and R is the effective. Now here, many people make mistake. When you do this one, finally you are going to get 1 upon R, and then after that we have to take the reciprocal of that one, and that will be your final answer. So don't just do 1 upon R1, 1 upon R2, 1 upon R3. Once you get that combination, remember, that's not your final answer, that's 1 upon final answer. So whatever answer you are going to get, you have to further take the reciprocal to get the final answer of the effective combination of the parallel resistances. Resistor can be itself fixed, which is like the first one, or it can be variable. In that case, the variable resistance will be denoted either by this one, by an arrow. In general, arrow represents something which is something variable in nature. Another option is if you have a potentiometer or rheostat, then to indicate that this arrow can be slided physically in real life. You can actually slide that arrow, and depending upon how much length you are including or excluding, the value of that resistance increases or decreases. So because of that, this arrow represents variables resistor. With this one, let's go to the next subtopic, which is the heating effect of electric current. We normally use in specific resistances, specific applications. For example, we have the electric heater to heat, let's say, a bucket of water. So in that case, the electric power is given by multiplication of voltage times current, and the energy supplied will be voltage times current multiplied by time. The units of electric power will be watt, again name of a scientist, James Watt, and energy supplied, the unit will be joule, again name of a scientist, and that will be power multiplied by time. Power is V times I, V is voltage, I is current, so the formula will be voltage into current into times. Let's see a couple of quick examples. In case of 4 wires with same material, we have been given 4 situations, and they have asked us in which scenario the resistance will be minimum. We know that, let's see 4 scenarios, part A, B, C, D. We know that these are the individual scenarios. The first one is the diameter, which is variable. In this first case, it is d by 2, second case is d by 4, third case is 2d, and fourth case is 4d. And the length itself is different in all 4 scenarios. In the first case, it is L by 4, second is 4L, third is L, and the last one is 2L. The question is, which of these 4 combinations is going to give you the minimum resistance? We know that the overall resistance of the conductor is dependent on its specific resistance multiplied by length of that conductor and divided by area of cross section. So if you do that, let's write that same formula for all 4 scenarios, and I'm going to substitute L as L by 4 in the first case, and A, which is circular cross section, so pi by 4 d square. Actually it's pi r square, but pi by 4 d square. So in case of diameter, I'm going to represent d by 2. If you simplify that one, or if you write that for all 4 scenarios, now if you will notice that since the material is same, rho is going to be same for all 4 scenarios, and pi by 4 is just a constant, so that's going to be constant everywhere. So that's not going to create any differentiation. So let's assume that rho divided by pi by 4 is just a number. We don't care about it because that's going to be uniform in all 4 scenarios. So let's assume that rho divided by pi by 4 is just constant k. So in the first case, it will be k, which is rho divided by pi by 4, and then L by 4, and then d square by 4. Remember, this by 2. So when you square it, it will be divided by 4. So divided by 4 divided by 4 by 4 by 4 will get cancelled, and eventually it will be L divided by d square. So that will be the effective resistance of the first scenario. Let's repeat the same thing. Here it will be d square by 16, but that by 16 will come in the numerator. It will become 64 L by d square. K will remain as it is. If you do that for remaining things, this will be L divided by 4d square. Remember, this pi by 4 and rho, we are going to combine that in one single constant. And let's repeat that for the last scenario. It will be 4d square will be 16 and 2L divided by 16, that will be simplified as 1 upon 8. So now if you compare all these 4 scenarios, what is the question? Minimum. So in this case, this is standard, this is actually higher because this is 64 times, this is lower because this is divided by 4, but this is divided by 8. So this is actually the least resistance. Now in actual exam there will be different set A, set B. So they create small variation. You might have seen this example, and some sets they have C as an answer, but there the numbers are different, scenarios are kind of shuffled, the values are changed. So I suggest you to use the formula, substitute, plug in the values, and then decide which one is the lowest, which one is the highest, depending upon what has been asked. So the final answer for this question will be option D, because that's the lowest, because this is divided by 8. Let's see one more example. This is not multiple choice question. This is draw a schematic diagram. We are supposed to draw a schematic diagram of a circuit, and that consists of a battery of 4 dry cells. That's one thing, and each dry cell is worth 1.5 volt. So altogether it will be 1.5 times 4, so that will be 6 volt. There are 3 resistors, one is 2 ohm, one is 6 ohm, and one is 16 ohm. They are connected all in series with a plug key. So everything is connected end to end, nothing complicated as such. And on top of that, we have to draw an ammeter, which is used to measure the current. Remember, ammeter is always connected in series and voltmeter is connected in parallel. That voltmeter is connected across only 16 ohm to measure the potential difference. And then after drawing the circuits, we are supposed to solve these 2 sub questions. So let's see the diagram. First of all, there are 4 batteries, each worth 1.5. So total it will be 6 volts. We are supposed to show all 4 bigger lines on the left, or you can show all bigger 4 lines on the right. But you must be consistent. You cannot mix and match, otherwise these voltages will get subtracted rather than getting added. So all 4 left bigger lines on the left, or all 4 bigger lines on the right. The key is now you can show a close key or open key, but they have specified in the part B when the key is closed. So I will prefer something with a dot in the center. This is the key element. Then the 3 resistors will be 2 ohms, 6 ohms and 16 ohm. They will be end to end, so they will be connected in series. And ammeter is always in series. Voltmeter is supposed to be connected in parallel, and that has to be connected only for 16 ohm. So this will be your schematic representation of the circuit. Now current flows from positive terminal to negative terminal. So if you want, you can show an arrow going from positive side, eventually going towards the negative side. So this will be your direction of current. Remember, here the longer lines were on the left, so they represent positive terminal. So that's why the arrow was going from left, eventually ending towards right. If you show the longer lines towards right, then the flow of electron, the flow of electricity will be exactly opposite. So this arrow and what you are showing in the battery, they have to be a little bit consistent, otherwise you may be deducted some points. Now that will be your complete circuit. Let's go to the actual question, ammeter reading. Now we want to ammeter voltage, ammeter measures current. Since these 3 are in series, the total resistance will be 2 plus 6 plus 16, that will come out to be 24, and the voltage is 6 voltage. So current is voltage divided by resistance, 6 volt divided by 24 ohm. So that will be 0.25 ampere. So that will be the answer for the first sub question. Now second sub question is voltmeter reading when key is closed. Now voltage equal to current times resistance. Now we are concentrating only on this part. We know that the current is uniform, constant throughout the circuit. The current flowing is, we have already calculated as 0.25, and the resistance only for this thing is 16 ohms. So we are going to multiply 0.25, which is ampere, times 16, which is ohm, and altogether it will be 4 volt, and that will be your answer for the second sub question. Now, while we are on this topic, let's briefly revise 12th chapter also. Let's say when we have magnetic effect of electric current is capable of producing magnetic effect, and vice versa, these two things are kind of correlated. When you have a magnet, this is like bar magnet, it has two poles, north and south, and this is iron powder or iron filling, so they will be attracted to that magnet. Now, if you want to show some magnetic lines, you have to be a little bit careful. Magnetic lines, they originate from north pole, so they will be originating from north pole and eventually terminating at the south pole. Now, some care has to be taken when we show these lines. These lines can be curved, the lines can be straight, it depends, the curvature depends upon the strength and the distance and all those things. That's not an issue. The issue is the magnetic lines, they should never cross over or they should never intersect. So if you trace a line, you will not find it crossing, just like an alphabet X. That does not happen, so that will be wrong. And sometimes you show magnetic field like this one, where the arrows actually indicate in which way the lines are going, so that if you draw a tangent, that will become this arrow. Again, these are different representations, but these basic things must be followed when you show a magnetic field with the help of these curved lines. Now, there is a right hand rule. Right hand rule says that if you stretch your thumb and if you curl the remaining 4 fingers, the thumb gives you the direction of the current. Here I is the current and B is the magnetic field. So if the current is being carried in this conductor in a linear manner, then the magnetic field developed will be kind of with curvature, and if you stretch your thumb to align with the direction of the current, then the curved direction of the remaining 4 fingers gives you the direction of this magnetic field. And this can be reverse also. If the thumb is going up, it will be like this one, or you can actually reverse the thumb also, and that will give you exactly opposite sense of magnetic field. Instead of getting clockwise from top, you will get anti-clockwise or counterclockwise from top when you reverse the direction of the current. There is another rule, magnetic field due to current rule. Now, what's the difference between this and this? Here the current is linear and the magnetic field is curved, and here it is exactly opposite. Here the current is in the coil, which is like with having some curvature due to that coil, and the magnetic field is linear. So you can say these are exactly opposite of each other. Who is linear and who is with the curvature, that decides what rule you are going to follow. There is another rule called Fleming's left hand rule, and that involves, first of all, as the name suggests, it's with the left hand, and it involves 3 fingers. The thumb indicates you the direction of the force, and the index finger actually gives you the direction of magnetic field, and the middle finger gives you the direction of current. These 3 have to be stretched fully such that they are mutually perpendicular to each other, and then each finger represents according to this Fleming's left hand rule. Domestic electric circuits is like what we use in real life in our house. We use AC circuit. Remember, there are 2 types of electricity. One is a DC, which is created by battery or dry cell. As opposed to that, what we use in real life in our house is AC. AC stands for alternating current, where the waveform is actually not flat. In DC it is flat. In AC it's like sinusoidal, means it's with the sine wave. There are reasons why this is sine wave, because of the generator continuously rotating, but that's kind of advanced. If you take electrical engineering, you will study the reason and advantages of AC over DC. But for the time being, remember that AC is a fluctuating or sine wave, as opposed to DC, which is direct current, which is more or less constant.
In our house we use AC circuit. It's actually 220 volts with 50 hertz. Hertz is a symbol for unit for measuring frequency. Hertz is nothing but cycles per second. So in 1 second the electricity fluctuates 50 times in 1 second. In India we use this combination. In other countries it can be slightly different combination. We can have 110 volts, you can have 60 hertz. So but in India we use 220 volts and with 50 hertz. We use 3 lines. One is with the red insulation, that's live wire, equivalent of positive. Black insulation is neutral wire, and green insulation is the earth wire. Right. So this is the sign conventions and color coding which we follow, at least in India. That's all for the time being. Remember to check our channel for more details and more videos. Our YouTube channel periodically keeps on posting revision videos and solutions. Also, please visit our website vidyanti.com, which has AI generated homework solutions as well as a lot of other information solutions. And if you like this video, please leave a comment, share with your friends, and if you have not subscribed already, please consider subscribing. And that's all for the time being. This is Prashant sir, recording live for vidyanti.com. Thank you very much. All the best. See you soon.